All right, let's jump right into this explainer. Today, we're tracking a truly fascinating scientific pipeline, looking at how a disastrous farm plague was meticulously reverse-engineered into one of the world's most prescribed, life-saving medications.
I mean, it sounds like a complete mystery, right? How exactly does a deadly agricultural accident, specifically spoiled cow feed, become a potent rat poison, and then eventually transform into a daily pharmaceutical taken by millions to prevent heart attacks and strokes? Well, we are going to solve that mystery right now.
The story actually begins out on the farm. Throughout the 1920s, this strange and bloody illness started slowly spreading through cattle farms all across North America. Farmers were watching in absolute horror as their perfectly healthy cows would suddenly collapse, fatally hemorrhaging after totally routine procedures. The big break in the case didn't come until a severe Wisconsin blizzard in February of 1933. A deeply frustrated farmer named Ed Carlson drove 200 miles through the snow to the University of Wisconsin. He literally walked into a lab carrying a dead cow, a bucket of its unclotted blood, and a pile of moldy sweet clover hay, and he demanded a solution.
To understand how this all unfolded, we're going to use this incredible story as a tutorial to see exactly how scientific research moves from the farm to the pharmacy. Our roadmap for today is 1. The problem on the farm. 2. Isolating the culprit. 3. The biochemical saboteur. 4. Patents and pest control. 5. The pharmaceutical breakthrough. And finally, 6. The future of dosing.
Okay, starting right off with Section 1, the problem on the farm, identifying the cause. You have to appreciate the sheer persistence required in early scientific research. When Ed Carlson dropped that bloody bucket on the floor in 1933, biochemist Carl Paul Link and his students immediately got to work. But, it wasn't an overnight success story. It took 6 long years of tedious work just testing hay samples to finally isolate the compound causing the bleeding, a substance called Coumarin. By 1940, they had successfully synthesized it, and by 1948, it was officially patented.
Which brings us right into Section 2, isolating the culprit, finding analog 42. So Link's team actually synthesized over 100 related compounds, desperately looking for the absolute most potent version. And the clear winner was a molecule they simply labeled analog number 42. They figured out that certain molds in wet hay were essentially converting coumarin, which is a harmless, slightly bitter substance found in plants like cinnamon and sweet clover, into this incredibly deadly anticoagulant. Link named analog 42 Warfarin to honor the Wisconsin Alumni Research Foundation, or WARF, since they funded and patented all this crucial work.
But how does this molecule actually do its damage? Let's move to Section 3, the biochemical saboteur, how it stops clotting. The key here is understanding exactly how your blood naturally clots. Our bodies rely on a super delicate process known as a molecular cascade. Imagine a perfectly timed sequence of falling dominoes. Almost 30 different enzymes and proteins have to act one right after the other to change your blood from a free-flowing liquid into a gel which forms a life-saving plug at the exact site of an injury. If you disrupt literally just one of these dominoes, the whole cascade stops dead, and the bleeding continues.
Let's break this down with a simple analogy. Think of your body's clotting system like a normal, functioning factory. In this factory, vitamin K is the manager, and its job is handing out sticky tools so proteins can bind calcium and successfully build those blood clots. But when Warfarin enters the system, you suddenly have a sabotaged factory. Warfarin acts as a molecular saboteur that specifically targets an enzyme called VKORC1, effectively locking that vitamin K manager entirely out of the building. Without those sticky tools, the proteins are basically useless, and clot production just halts completely.
Once they fully understood its immense power, they needed a practical application. That's Section 4, patents and pest control, from lab to market.
Because warfarin was just so incredibly lethal to small animals, its very first commercial application wasn't actually medicine at all. No, it was extermination. By 1950, it hit the market as a wildly successful rat poison. It was water-soluble, it was super easy to mix into bait, and it worked flawlessly. In fact, the proceeds from this pest control application ended up funneling millions of dollars right back into the university to fund even more scientific innovation. But scientists like Link, they always suspected that what stopped a cow's blood from clotting might also prevent deadly blood clots in humans.
Now we'll see how this leads to an unexpected, truly monumental pivot in medical history. Section 5, the pharmacy breakthrough, an accidental trial.
In 1951, a U.S. Navy recruit who was struggling with depression attempted to take his own life by ingesting multiple, huge doses of a warfarin-based rat poison. He arrived at the hospital in severe pain, bleeding internally. But because the doctors already understood the underlying biochemistry, they knew warfarin simply blocked vitamin K, they immediately treated him with massive doses of vitamin K alongside blood transfusions. And to everyone's absolute shock, the young man made a complete, speedy recovery.
So, this tragic event inadvertently acted as a highly successful human trial. It proved beyond a shadow of a doubt that warfarin's effects were safely and easily reversible in humans. The exact same chemical that served as the world's premier rat poison could actually be safely administered to humans to thin their blood. By 1954, warfarin was officially approved for human medical use under the brand name Coumarin, and that created this mind-bending reality, a heavy-duty pest control solution sitting right alongside a daily life-saving pink medicinal pill.
That brings us to the final step in our pipeline. Section 6, the future of dosing, personalized medicine. Even though warfarin became a medical staple for over 6 decades, it definitely earned a reputation as an incredibly tricky drug to prescribe. I mean, some patients needed tiny doses, while others needed massive ones just to prevent clotting. Why the huge difference? Well, decades later, the Human Genome Project finally solved this mystery. Modern pharmacogenetics revealed that our DNA dictates exactly how we handle the drug. Mutations in the CYP2C9 gene change how fast your liver clears the drug, while mutations in the VKORC1 gene change how sensitive your specific enzymes are to it. Combine all that genetics with diet, age, and weight, and you realize pretty quickly that prescribing warfarin requires a highly personalized approach.
And just look at the overall result here. This entire pipeline, from a dead cow on a snowy farm, to a lab isolating a moldy chemical, to an accidental human trial, and finally to modern genetic dosing, has had a staggering impact. Warfarin has been used for over half a century to prevent fatal pulmonary embolisms, protect stroke and heart attack survivors, and keep blood flowing properly in post-surgical patients. It has literally saved millions of lives globally.
I want to leave you with this fantastic quote from Carl Paul Link, the very same scientist who first took in that farmer's moldy hay back in 1933. Reflecting on his massive discovery, he just said, a pretty bad thing for rats, but a good thing for humans. It's quite the understatement, and it begs an incredible question. As we look around our natural world today, what other miraculous, life-saving solutions are just hiding in plain sight, waiting for the right scientist to reverse engineer them?